100 billion stars. That is what our galaxy holds. For generations, that number has carried weight, the kind of weight that made us feel enormous, significant, perhaps even central to something grand. James Webb just changed that. In a single image, Webb stared into a patch of darkness, so small it would be covered by a grain of sand held at arm's length, and it found thousands of entire galaxies packed inside that void. Not a handful, not dozens, thousands, each one holding hundreds of billions of stars of their own, some holding trillions. We are going to travel from the edge of our own galaxy to the farthest light James Webb has ever captured. We will visit galaxies that should not exist. We will pass through voids so enormous they strain the mathematics used to describe them. We will encounter structures so ancient, so massive, and so early in cosmic history that they are actively forcing scientists to question the models they spent decades building. And by the end of this journey, the number 100 billion, a number that once felt staggering, will feel like something else entirely. Stand outside on a clear night and look up. If you are somewhere far from the blurred orange glow of a city, if you are out in the open somewhere dark and still, you might see it. A faint, pale ribbon of light smeared across the sky from one horizon to the other. It does not look like much. It shimmers slightly, like something left behind, like the ghost of something larger. That pale band is our galaxy. Every individual star you can see with your naked eye, every single point of light you can make out without a telescope or binoculars, belongs to it. All of them. The ones that burn steady and the ones that flicker. The blue ones, near the belt of Orion, and the reddish one at the shoulder, all of them live inside the same galaxy you do. For thousands of years, that smear of light was the entire universe. Not metaphorically, literally. As far as any human being on Earth understood, that pale ribbon was all there was. It felt vast. It felt overwhelming. It felt, in the way that only genuinely enormous things feel, complete, like there could not possibly be anything more. Like the universe had handed us everything it had, and we were only beginning to make sense of it. We now know it is neither complete nor particularly vast, not compared to what surrounds it. The problem with studying our own galaxy has always been one of position. We are inside it. Imagine trying to draw a detailed map of a city while standing in the middle of its most crowded intersection, surrounded by buildings in every direction, crowds moving through every gap in your vision. You can see what is directly around you. You can make educated guesses about what lies beyond the buildings to the north or the south. But the full picture, the layout of the streets, the pattern of the neighborhoods, the shape of the city as seen from above, stays hidden. Not because the information does not exist, but because you are too embedded in it to gain the perspective you need. That is exactly the challenge astronomers have faced for centuries when trying to understand the Milky Way. We live inside the thing we are trying to measure, and it is not a small, simple thing we are trying to measure. It is a galaxy, a rotating, swirling, dust-choked structure of hundreds of billions of stars spread across a distance that would take light itself 100,000 years to cross from one side to the other. Ground-based telescopes helped in the early decades of serious astronomical study. Researchers were able to identify that we live inside a disk of stars, that the disk has a bulge at its center, and that we sit roughly 2/3 of the way out from that center, along one of several curving arms. Then the Hubble Space Telescope pushed further, giving astronomers a tool capable of peering past the immediate stellar neighborhood and beginning to chart more distant regions. Scientists mapped large sections of our galaxy using radio waves and infrared light, forms of radiation that can penetrate the dense clouds of dust and gas that block visible light in many directions. They built sophisticated models. They calculated the number of spiral arms, estimated the diameter, tracked the orbital motion of stars near the galactic center. The picture improved slowly, carefully, piece by painstaking piece. By the early 21st century, the scientific consensus had settled around a figure. Our galaxy spans roughly 100,000 light-years across. Some measurements pushed that estimate higher, closer to 150 or even 200,000 light-years, when the outermost reaches of the stellar halo were included. But the core figure, the number most commonly used, was 100,000 light-years. That number was supposed to feel enormous, and for a long time it did. 1 light-year alone is approximately 6 trillion miles. A single light-year is the distance light covers in a full year, travelling at roughly 186,000 miles per second. Multiply that 6 trillion mile figure by 100,000, and the number you get is so far beyond normal human intuition that it essentially stops being meaningful in any everyday sense. We have no physical experience to anchor it to. We cannot drive it, walk it, or visualize it in any direct way. It simply stands there enormous, abstract, incomprehensible in scale. Then James Webb launched. Webb was not designed specifically to study the Milky Way. Its primary mission was directed outward toward the deepest, oldest, most distant regions of the observable universe. Webb was built to see things Hubble could not, objects too faint, too far, or too heavily redshifted into infrared wavelengths for any previous instrument to detect. In doing so, however, it accidentally, or perhaps inevitably, reframed everything about how we see and understand our own galaxy. Because the moment Webb began returning images of what lies beyond the Milky Way, the scale comparison became impossible to avoid. In one of Webb's confirmed deep field images, the telescope captured thousands of galaxies in a region of sky so small it would be covered by a single grain of sand held out at arm's length. Not thousands of stars, thousands of entire galaxies. Each of those galaxies contains anywhere from tens of billions to several trillion stars of their own. Some are spiral-shaped, structured much like ours. Others are elliptical, bloated and round, built from the mergers of earlier systems. Others are irregular, distorted, stretched into shapes we have no clean, simple name for. All of them are complete, independent island universes. Systems so vast that light takes tens of thousands of years just to cross them. And our galaxy, the one we live inside, the one that seemed so enormous when we were first trying to measure it, is simply one among them. One entry in a list that now extends to the trillions. The Milky Way is classified by astronomers as a barred spiral galaxy. It has a central bar structure, a dense, elongated region of tightly packed stars running through the core, with several large spiral arms curving outward from the ends of that bar. From above, it would look something like a slow-spinning, luminous pinwheel, glowing brightest at its center and becoming progressively sparser and more transparent toward its edges. Scientists are confident about the general shape and structure. The exact number of major spiral arms and their precise geometry is still being refined, as is common with a system we are studying from the inside. But the broad picture is well established. What Webb made undeniable is that this galaxy, for all its complexity, for all its hundreds of billions of stars, for all its vast internal distances, occupies a tiny corner of something almost incomprehensibly larger. The view from inside feels grand. The view from outside tells a completely different story. To understand just how completely Webb changed the story, it helps to go back to a moment 30 years earlier. A moment that was itself supposed to be revolutionary, and was but now looks, in retrospect, like only a first step. In 1995, astronomers made a decision that many of their colleagues thought was reckless at best and wasteful at worst. They pointed the Hubble Space Telescope at a tiny patch of sky near the Big Dipper, a region chosen specifically because it appeared completely empty. No nearby stars, no known galaxies, nothing visible to any instrument then in operation. The patch of sky they selected was so small and so devoid of anything detectable that pointing a telescope at it felt to many researchers like deliberately pointing a camera at a blank white wall. Colleagues pushed back. Why waste 10 consecutive days of irreplaceable telescope time staring at nothing? There were hundreds of known objects worth studying. There were active questions about galaxies already detected, clusters already mapped, phenomena already underway that deserved observation time. Pointing Hubble at an empty rectangle of sky seemed to a significant portion of the astronomical community like a serious misallocation of resources. Hubble stared for 10 days anyway. What came back changed everything. That apparently empty patch of sky contained more than 3,000 galaxies. Not 3,000 stars, 3,000 complete, independent galaxies, each one a system of hundreds of billions of stars, each one separated from its neighbours by distances measured in millions of light years. The image became known as the Hubble Deep Field, and it became one of the most consequential photographs in the history of science. Not because of what it showed, though what it showed was extraordinary, but because of what it implied. If one tiny, carefully chosen, deliberately blank piece of sky contained 3,000 galaxies, then the universe was not sparsely populated. It was not half full or mostly full. It was saturated. It was packed in every direction, at every depth, with structure. That was a powerful and genuinely disorienting moment. Humanity had just learned that emptiness was not empty, that darkness was not dark, that every direction you could possibly point any telescope contained galaxies, not maybe, not probably, but certainly. But Webb went further. When James Webb Space Telescope turned its instruments toward a similar patch of deep sky, it did not simply replicate what Hubble had found. It did not match the result or modestly improve on it. It demolished the comparison. Webb's primary imaging capability uses infrared detectors instruments sensitive to wavelengths of light far beyond the red end of the visible spectrum. This matters enormously for deep field astronomy because as the universe expands, light from the most distant galaxies is stretched. The original wavelength of that light, often ultraviolet or visible, gets pulled by the expansion of space itself into longer and longer wavelengths, eventually landing in the infrared range. Hubble, with its primarily visible light detectors, could not see those stretched wavelengths. Webb can, and what Webb found when it looked into the deep infrared was not just more galaxies. It was older galaxies, earlier galaxies, galaxies that formed when the universe was young, in a way that stunned researchers, not just for their existence, but for their nature. Webb's deep field images contain galaxies at distances so extreme that their light left before our own planet existed, before the sun existed, before the molecular cloud that would eventually collapse to form our solar system had even begun to contract. The light captured in a single Webb deep field image has been traveling through space for more than 9 billion years. Some of it has been traveling for more than 13 billion years emitted when the universe itself was less than 1 billion years old, perhaps much less. Think carefully about what that means. The light Webb catches is not showing us those galaxies as they are now. It is showing us those galaxies as they were, billions of years ago. When the universe was young and dense and running at full intensity in a way that has since faded. Webb is not a telescope in any simple conventional sense. It is a time machine. Every image it returns is a window into a moment that no longer exists, a preserved fossil of light that has been travelling through expanding space since long before anything alive on Earth had eyes to see it. The confirmed science here is remarkable and clearly stated. Webb's observations have detected galaxies at distances corresponding to redshifts that place their formation within the first few 100 million years after the Big Bang, the event estimated to have occurred approximately 13.8 billion years ago. Some of the galaxies Webb has detected formed when the universe was less than 5% of its current age. They were already assembling stars in large numbers, already gravitationally gathering into recognizable structures, already evolving along trajectories that surprised researchers who had expected early galaxies to be smaller, simpler, and less organized than what Webb found. And all of this is visible inside a patch of sky you could cover with a grain of sand. The question that follows from this discovery is both immediate and genuinely unsettling. If one tiny sliver of apparently empty sky contains thousands of ancient galaxies visible even to an instrument looking across more than 13 billion years of cosmic time, how many galaxies exist across the full observable universe? Astronomers had previously estimated the number at around 200 billion. After incorporating Webb's capabilities and revised detection models, some researchers now believe the true number, including galaxies too faint or too distant to directly image even with Webb, could be closer to 2 trillion galaxies. Each one a system of stars, gas, planets, dust, and dark matter. Each one evolving across billions of years, according to processes that are still not fully understood. Each one occupying a volume of space so vast that even the concept of distance loses its intuitive meaning at those scales. And our galaxy, the Milky Way, the one we live in, the one whose pale edge we see on a clear night, is simply one item in that catalogue, one entry among 2 trillion. Here is what makes this feel personal rather than purely abstract. Every photon of light in those Webb images travelled billions of light years before reaching a mirror the size of a large dining room table, floating silently in space at a temperature colder than anything in our solar system. That telescope did not generate that image. It did not create those galaxies or manufacture that light. It simply caught photons that had nowhere else to go, ancient light that had been travelling through expanding space since before our sun existed and just happened to arrive at the precise location where humanity had placed a mirror capable of receiving it. The universe was always this full. Every direction was always this crowded with structure and light and history. We simply lacked the instruments to see it. We lacked the mirrors, the sensitivity, the wavelength range, and the stability required to detect what was always there. Webb did not discover the universe. It revealed it. But knowing the universe is crowded with galaxies is only the beginning of what Webb is telling us. Because some of those galaxies Webb found should not exist. Not in any comfortable sense of that phrase. They formed too early, grew too massive too quickly, and arrived at levels of complexity that the models astronomers spent decades building had specifically predicted would not be possible that soon after the Big Bang. These galaxies are not minor anomalies at the edge of the data. They are prominent, clear, well-observed objects that sit in direct tension with theoretical predictions. And the question of how they got there, how the universe built them so fast, is one of the most active and genuinely uncertain questions in modern astrophysics. That is where things get strange. And that is exactly where we are going next. For most of human history, measuring the cosmos meant measuring what could be seen. Stars were identified by their positions and their brightness. Distances were estimated, poorly at first, from parallax, the slight shift in a nearby star's apparent position against the background of distant stars as Earth moves around the Sunday. The method worked for nearby stars, but broke down at the scales where galaxies began to matter. Then, in the early 20th century, everything changed. Astronomers discovered that certain types of variable stars that brighten and dim in regular cycles, have an intrinsic luminosity that is directly related to how long those cycles take. By measuring how long the cycle is, a researcher can calculate how bright the star actually is, and by comparing that calculated brightness to how bright the star appears from Earth, the distance can be derived precisely. These stars, called Cepheid variables, became the first reliable standard candles for measuring cosmic distances. Using Cepheid variables, Edwin Hubble measured the distance to a fuzzy patch of light that had been catalogued as the Andromeda Nebula. The distance he calculated was far too great for Andromeda to be part of the Milky Way. It was, in fact, an entirely separate galaxy, 100 billion star system in its own right, orbiting through its own region of space, approximately 2.5 million light-years from us. Hubble's measurement in 1923 effectively doubled and then multiplied many times over humanity's understanding of the scale of the universe. Overnight, the cosmos expanded from a single galaxy to a universe containing many. The philosophical shock was enormous. Everything people had thought of as the universe was actually just our neighborhood. Hubble went further. By measuring the distances to many galaxies and combining those distances with measurements of how fast each galaxy appeared to be moving away from us, he identified a pattern that has since been confirmed and refined into one of the central facts of modern cosmology. The universe is expanding. Every galaxy is moving away from every other galaxy, not because galaxies are traveling through space like bullets fired outward from a central point, but because space itself is expanding. The distances between galaxies grow continuously because the fabric of space between them is stretching. This expansion is described by what is called the Hubble constant, a number that relates the speed at which a galaxy appears to recede to the distance it is from us. The Hubble constant sounds simple in concept. In practice, it has become one of the most contentious measurements in modern physics, and Webb sits at the center of that controversy. Different methods of measuring the Hubble constant, different observational techniques using different types of objects as distance markers produce slightly but stubbornly different results. When researchers use observations of the early universe, specifically the cosmic microwave background radiation, the faint thermal glow left over from when the universe first became transparent to light, and run those observations forward through known physics, they get one value for the Hubble constant. When researchers use direct measurements of nearby galaxies, Cepheid variables, supernovae, and other local distance indicators, they get a slightly different value. The two values are close, but they are not the same, and the difference between them is larger than can be explained by measurement uncertainty alone. This discrepancy has a name, the Hubble tension, and it matters enormously because the Hubble constant is not just a number about expansion, it underpins estimates of the age of the universe, the size of the observable universe, and fundamental aspects of cosmological models. If the Hubble constant is slightly different from what either measurement suggests, then everything derived from it needs to be adjusted accordingly. Webb entered this conversation with a specific goal: to measure Cepheid variables with higher precision than Hubble could achieve in more distant galaxies with less observational noise. The hope was that Webb's sharper eyes would resolve the tension by showing that one set of measurements had a systematic error, the other did not. The expectation for many researchers was that Webb would confirm the local distance ladder measurements and thereby identify the problem as lying in the early universe calculations. That is not what happened. Webb's Cepheid measurements came back with higher precision, and the local measurements remained inconsistent with the early universe value. Webb sharpened the numbers. It did not resolve the tension. If anything, it deepened it by removing one of the most natural explanations, measurement imprecision, without providing a replacement. The Hubble tension now sits as a confirmed, precision measured discrepancy between two robust methods of determining one of the universe's most fundamental quantities, and no currently accepted explanation fully accounts for it. This is not a catastrophe for cosmology. It is not the beginning of the end for the Big Bang model. The overwhelming majority of cosmological observations, the distribution of galaxies across cosmic time, the pattern of the cosmic microwave background, the abundances of light elements, the large-scale structure of the cosmic web remain in excellent agreement with the Standard Model. But the Hubble tension is real. It is measured carefully, and it suggests that either one of the two measurement methods has a subtle, unidentified error, or that the universe contains some physics not yet incorporated into the Standard Model. Both possibilities are taken seriously. Neither has been resolved. The Hubble tension is one kind of challenge Webb has introduced to established theory. The early massive galaxies are another kind entirely, and arguably the more dramatic one. The Standard Model of cosmic structure formation, sometimes called lambda CDM, where CDM stands for cold dark matter, makes specific predictions about how galaxies should have formed and grown over cosmic time. In the earliest moments after the Big Bang, matter was distributed almost uniformly through space. Almost, but not quite. There were tiny fluctuations, quantum-level variations in density that were amplified by the rapid early expansion of the universe. Over time, gravity acted on those fluctuations. Regions that were very slightly denser than average began to attract more matter. Dark matter, which does not interact with light and cannot be observed directly, but does respond to gravity, clumped first, forming what cosmologists call Halo's invisible gravitational structures that acted as the scaffolding for the visible universe. Ordinary matter fell into those dark matter halos, cooled, condensed, and eventually formed stars. Those first stars formed in small clusters. Clusters merged into proto-galaxies. Proto-galaxies merged and grew into the galaxies we recognize today. This process takes time. In the lambda CDM model, Building a truly massive galaxy, one containing hundreds of billions of stars with a well-organized structure, requires multiple generations of mergers, billions of years of star formation, and a significant portion of cosmic history to unfold. Large galaxies, in the Standard Model, are predominantly a late universe phenomenon. The very early universe, by contrast, should be dominated by small, irregular, immature proto-galaxies still in the early stages of assembly. Webb looked into the early universe and found something different. Among Webb's most discussed findings are objects now referred to informally by both researchers and science journalists as the impossible galaxies. These are galaxies detected at extreme redshifts, placing them in the universe's first few 100 million years, that appear to be far too massive, far too organized, and far too mature for the Standard Model to easily accommodate. One category of these objects is referred to in the literature as massive quiescent galaxy systems that have already formed enormous numbers of stars and have already stopped forming new ones, a state that typically requires billions of years of star formation history to reach. Another category consists of galaxies that appear, from their spectral signatures and morphology, to be structured disk galaxy systems with organized rotation and distinct features at epochs when the universe was still too young, according to Lambda CDM, to have produced such order. These findings have not been rejected. They have been confirmed by multiple independent observing teams using different analysis methods and different Webb instruments. The objects are real. The distances are real. The apparent masses are real. What remains uncertain is precisely what they mean for the theoretical framework. Several explanations are being explored. One possibility is that the star formation rate in the early universe was significantly higher, more rapid, and more efficient than the Standard Models predicted. If the very first stars formed quickly and burned brilliantly, producing the raw material for subsequent stellar generations at a faster pace than expected, then early galaxies might have accumulated stellar mass faster than the models allow. Another possibility involves the behavior of dark matter in the early universe specifically. Whether the assumptions built into the Lambda CDM model about how dark matter behaves on small scales and at early times are fully accurate. A third possibility, the most radical and least favoured but not yet dismissed, is that some aspect of the physics governing the very early universe is genuinely different from what the current model assumes, that there is a missing ingredient, some process or particle or interaction not yet identified, that accelerated structure formation in ways the Standard Model does not capture. None of these explanations has been confirmed. None has been ruled out. The scientific community is working through the implications carefully, as it should, and as it always does when data and theory conflict at a meaningful level. What Webb has done is not topple the Standard Model. It has not come close to doing that, but it has identified specific, well-measured anomalies that the model currently does not satisfactorily explain. That is what science looks like when it is working correctly. Data leading theory into new territory, theoretical models scrambling to either accommodate the new observations or to identify where they themselves need revision. While the early universe anomalies command the most dramatic headlines, Webb has also been quietly revising our picture of things much closer to home, including the structure of our own galaxy. The Milky Way presents a specific observational challenge that astronomers have been working around for decades: the zone of avoidance. This is a strip of sky running along the galactic plane, the midline of our galaxy's disk, as seen from our position inside it, where the density of dust and gas is so extreme that visible light from objects beyond it is completely blocked. Trying to observe distant galaxies or other structures through the zone of avoidance using visible light telescopes is like trying to see the other side of a room through a solid concrete wall. The photons do not make it through. Entire regions of the sky portions of the celestial sphere that should contain galaxy clusters, individual distant galaxies, and other large-scale structures have historically been invisible to us, not because nothing is there, but because our galaxy itself is in the way. Webb's infrared instruments change this calculation significantly. Infrared wavelengths penetrate dust far more effectively than visible light. Where optical telescopes are completely blocked, infrared instruments can see through not perfectly, not at all wavelengths equally, and not without difficulty, but enough to reveal things that were previously completely hidden. Astronomers are actively using Webb to probe regions of sky that were previously in the zone of avoidance, building a more complete picture of what lies in those directions and how our galactic neighborhood connects to the larger cosmic structure around us. This work is ongoing, and the full extent of what it will reveal is not yet known, but the direction is clear. The zone of avoidance, which has distorted our maps of the local universe for as long as we have been making them, is becoming progressively more transparent. More broadly, Webb is contributing to the mapping of the large-scale structure of the universe in ways that complement and extend what was possible with previous instruments. The cosmic web, the vast network of galaxy filaments, clusters, and voids that describes the distribution of matter across the observable universe, has been known in broad outline for several decades. Built up from surveys using optical telescopes and later from radio and near-infrared data, but the early universe portions of that map have always been thin, imprecise, and based on limited samples. Webb is filling in those early epochs with actual detected objects, actual measured redshifts, and actual structural data, allowing researchers to trace the development of the cosmic web back to the earliest times for which it can be observed. What this map shows, when assembled across cosmic time, is remarkable. The large-scale structure of the universe, the pattern of filaments and voids, was already beginning to emerge in the very early universe. The seeds of the cosmic web were present in the earliest density fluctuations, and by the time Webb can detect structures within the first billion years, those seeds had already grown into recognizable protofilaments and protoclusters. The universe did not slowly and hesitantly begin to organize itself after billions of years of formless chaos. It began organizing almost immediately on timescales that push against the lower limits of what the standard model predicts, and in some cases appear to exceed them. Our galaxy is part of this structure. It is embedded in it, shaped by it, and its history is inseparable from the history of the cosmic web of which it forms a tiny node. Understanding the large-scale structure around us, which Webb is helping to reveal in unprecedented detail, is therefore not just an exercise in cosmic cartography. It is the context in which our own galaxy's existence makes sense. The Milky Way did not form in isolation. It formed within a web of dark matter and baryonic matter that had been assembling since the universe was microseconds old. Every star in our galaxy, including our Sun, is the product of that long, interconnected history. To truly grasp what Webb has revealed about the size of the universe and our place within it, it helps to do something that human beings are instinctively reluctant to do. It helps to start not with what is near and familiar, but with what is largest and most remote, and then work inward, layer by layer, until we arrive at home. Because arriving at home by that route, after travelling through the full structure of what surrounds it, produces a kind of understanding that no amount of number quoting can replicate. The numbers are important, but the journey through them is what makes them real. Begin at the largest scale currently accessible to observation. The observable universe, the sphere of space from which light has had enough time since the Big Bang to reach us, spans approximately 93 billion light-years in diameter. That figure already requires a moment of careful attention. The universe is 13.8 billion years old. One might expect that the observable universe, being bounded by how far light can travel in that time, would therefore span only 27.6 billion light-years, 13.8 in each direction. But space itself has been expanding throughout that entire time. Light that left a distant source shortly after the Big Bang has been travelling through space that was simultaneously stretching, carrying the source farther away even as the light moved toward us. The combined effect is that the source from which that ancient light originated is now accounting for all that expansion, located approximately 46 billion light-years away from us, in every direction. The observable universe is therefore a sphere with a radius of about 46 billion light-years, a diameter of about 93 billion, and a volume beyond any number that communicates anything useful in ordinary language. Inside that sphere, 2 trillion galaxies or something approaching that estimate, distributed not randomly, not smoothly, but in the intricate pattern of the cosmic web. Filaments of matter hundreds of millions of light-years long, connecting nodes where the densest clusters of galaxies accumulate. Between those filaments, voids regions of space nearly empty of galaxies, some of them hundreds of millions of light-years across, where the expansion of the universe has evacuated matter over billions of years and left behind a near-perfect approximation of nothing. The largest confirmed voids in the observable universe are structures so vast that naming them feels almost meaningless. The Botez void, for instance, is a region roughly 330 million light-years in diameter. If our entire local supercluster itself, 500 million light-years across, were placed inside the Botez void, it would have room to rattle around. The void is not a hole in the universe. It is a feature of it, a predictable consequence of how matter clusters and evacuates over cosmic time. But standing at its conceptual edge and looking inward, the scale of emptiness it represents is difficult to hold in mind. The cosmic web is the largest confirmed structure in the universe. It has no outer boundary that means anything beyond the limits of observation. It simply continues as far as can be detected in every direction. Webb's contribution to mapping this structure is to extend the observable range of the map backward in time toward the early universe, where previous instruments could detect the web only in its crudest outline. Webb is filling in the details of the web at high redshifts, at early cosmic times, with a resolution and completeness that transforms the sketch into something approaching an actual portrait. What that portrait shows at high redshifts is, again, surprising in ways that challenge simple expectations. The cosmic web appears to have been organizing itself earlier and perhaps more efficiently than standard models of structure formation predicted. Protoclusters. The seeds of the great galaxy clusters that dominate the nodes of today's cosmic web have been detected by Webb at distances corresponding to epochs less than 2 billion years after the Big Bang. These protoclusters are large, dense, and already in the process of drawing in surrounding galaxies at rates that imply a faster pace of structural assembly than the models comfortably accommodate. The Webb was not slowly emerging from the chaos of the early universe. It was apparently running ahead of schedule. Now move inward. Scale down from the cosmic web to one of its largest individual nodes, one of the great galaxy superclusters that anchor the filaments at their intersections. Our galaxy belongs to a supercluster. All galaxies do. Every galaxy in the observable universe is embedded in some large-scale structure, either a filament, a wall, or one of the great concentrations of matter at the Webb's nodes. Our supercluster is called Laniakea. The name comes from a Hawaiian phrase meaning immeasurable heaven, and it was chosen with a clear sense of the scale it was meant to evoke. Laniakea was formally defined and described in a landmark 2014 study that used the motions of galaxies, specifically the way gravity from large concentrations of mass causes galaxies to flow toward those concentrations, to map the boundaries of our local supercluster. The result was the identification of a coherent supercluster structure approximately 500 million light-years across, containing the mass of roughly 100 million billion suns, and encompassing more than 100,000 individual galaxies flowing, under the influence of gravity, toward a central gravitational focus known as the Great Attractor. 500 million light-years. Let that sit for a moment. The distance light covers in 500 million years of continuous travel at 300,000 kilometers per second. Laniakea is not a galaxy. It is not even a cluster of galaxies. It is a supercluster, a structure of clusters, themselves structures of groups, themselves structures of individual galaxies. The hierarchy of containment runs 4 levels deep before it gets to individual galaxies. The Great Attractor that anchors Laniakea is itself a remarkable object, or more accurately, a remarkable region. It is an area of space toward which everything within Laniakea appears to be gravitationally flowing, including our own galaxy, which is currently moving toward it at roughly 600 kilometers per second. The Great Attractor sits in a direction that is, for optical telescopes, squarely within the zone of avoidance buried behind the plane of our own galaxy, where dust and gas block the view. For most of the 20th century, astronomers knew something large was there because of the way galaxies were moving, but they could not see it directly. Webb's infrared capabilities, along with X-ray telescopes not blocked by optical dust, have helped to reveal more of the structure in this direction, though the full picture remains partially obscured and actively studied. What lies at the Great Attractor, insofar as it can be characterized, is a massive concentration of galaxy clusters, most prominently the Norma cluster and the Centaurus cluster, that together produce a gravitational pull strong enough to deflect the motion of galaxies across hundreds of millions of light years. The Great Attractor is itself likely being pulled toward an even larger concentration farther away, called the Shapley Supercluster, one of the largest accumulations of matter in the observable universe, located approximately 650 million light-years from us. The gravitational hierarchy runs deep. Laniakea is enormous, but it is one supercluster among many in the cosmic web. The Perseus Pisces supercluster, the Coma supercluster, the Shapley Supercluster. Each of these is a structure comparable in scale and complexity to Laniakea, and the observable universe contains uncountable thousands of them, arranged along the filaments and concentrated at the nodes of the web in a pattern that, at sufficiently large scales, begins to look almost biological, like the neural network of something vast beyond imagination, processing information across distances that defeat description, drop inward again. From Laniakea to the smallest structure embedded within it. Within Laniakea sits a significant cluster of galaxies called the Virgo cluster. The Virgo cluster is a dense concentration of more than 1,300 galaxies. Some estimates run considerably higher, centered roughly 53 million light-years from our own galaxy. It is dominated by several massive elliptical galaxies at its core, among them Messier 87, a galaxy containing a supermassive black hole whose image, more precisely, the shadow of whose event horizon backlit by accreting material, was captured in 2019 by the Event Horizon Telescope collaboration and became one of the most widely shared scientific images in history. The Virgo cluster is the gravitational anchor of the larger region called the Virgo Supercluster, sometimes called the local supercluster, a structure roughly 110 million light-years across that contains our galaxy and its immediate neighborhood. The Virgo supercluster is itself one of the subcomponents of Laniakea, located toward the outer regions of the larger supercluster rather than at its gravitationally dominant core. We are not centrally located in any of these structures. We are not at the center of the Virgo supercluster, not at the center of Laniakea, and not in any particularly prominent position within the cosmic web. We live in the outskirts of structures within structures, nested in a hierarchy that extends outward in every direction to scales we can observe but not visit, describe but not truly picture. Drop inward once more, from the Virgo cluster to the structure directly surrounding our galaxy. Our galaxy belongs to what astronomers call the local group, a relatively small collection of galaxies gravitationally bound together and moving through space as a unit. The local group spans approximately 10 million light-years and contains more than 50 galaxies. Most of these are dwarf galaxies, small, sparse, irregular systems containing millions rather than billions of stars, orbiting as satellites around the two dominant members of the group. Those two dominant members are our galaxy, the Milky Way and the Andromeda galaxy, designated Messier 31. Andromeda is our nearest large galactic neighbor. It sits approximately 2.5 million light-years away, a distance that sounds large and is large, but is small by the standards of the structures we have been traveling through. In galactic terms, Andromeda and the Milky Way are neighbors in a meaningful, gravitationally consequential sense. They are approaching each other. The two galaxies are currently moving toward one another at roughly 110 kilometers per second, and models of their trajectories predict a collision more precisely, a merger in approximately 4 to 5 billion years. It will not be a violent impact in the way the word collision implies in everyday contexts. Individual stars are so widely spaced within each galaxy that actual stellar collisions during the merger will be extremely rare. But the gravitational interaction will distort both galaxies dramatically, rearrange the orbits of billions of stars, likely trigger intense bursts of star formation as gas clouds are compressed by the interaction, and eventually, after multiple passes spanning billions of years, result in both galaxies merging into a single, larger elliptical galaxy. Astronomers have informally named this predicted future object Milky Way. The local group, for all its apparent richness, more than 50 galaxies, 2 large spirals, dozens of dwarfs, is a modest structure by the standards of what surrounds it. The Virgo cluster, one of the dominant concentrations in our local region of the cosmic web, contains more than 1,000 galaxies. The local group's 50 plus are a quiet corner of a quiet neighbourhood within a much larger and far more populated universe. And now, at last, inward to our own galaxy, to the Milky Way itself, 100,000 light-years across. That was the number settled on by early 21st century consensus, and it remains a reasonable central estimate for the diameter of the main stellar disk. More recent measurements, incorporating data on the outermost reaches of the galaxy's stellar halo, the extended, roughly spherical cloud of stars and globular clusters that surrounds the disk, push the total extent of the Milky Way's gravitational domain to estimates as high as 1.9 million light-years. The difference between those numbers, 100,000 for the disk, nearly 2 million for the full halo, illustrates something important about how we define the boundaries of a galaxy. There is no clean edge, no line where the Milky Way ends and empty intergalactic space begins. The galaxy fades at its outermost reaches into a sparse scattering of stars moving on wide, slow orbits through the galactic halo before eventually giving way to the void between us and the next gravitational domain. Within the disk, the Sun sits roughly 26,000 light-years from the galactic center, a little over halfway out from the core to the edge of the disk in a region called the Orion Arm, or sometimes the local arm. It is one of several spiral arms curving outward from the ends of the central bar. The Orion Arm is not one of the galaxy's primary spiral arms. Those are typically classified as the Perseus Arm, the Scutum Centaurus Arm, the Sagittarius Arm, and the Outer Arm. The Orion Arm is considered a spur or minor arm, a smaller, shorter feature connecting between two of the major arms. Our Sun is not in a particularly notable location. It is not in the densest part of the galaxy. It is not in the most star-rich region. It is not near the center, with its intense radiation fields and closely packed stellar populations. It sits in a relatively calm average region of a spiral arm of middling importance in a galaxy of average size and average mass. At the center of the galaxy, *roughly 26,000 light-years from where we are, sits a supermassive black hole. It is called Sagittarius A*, and its mass has been measured at approximately 4 million times the mass of our Sunday. It is surrounded by a dense cluster of stars, some of which orbit the black hole on highly elliptical trajectories that take them extremely close to the event horizon at their nearest approach. These stars, as they are called, have been used to measure the mass of Sagittarius A times with high precision, and their orbits were also used in the imaging effort that produced the 2022 Event Horizon Telescope image of the black hole itself, the first direct image of the supermassive black hole at the center of our own galaxy. Sagittarius A times is large by solar standards. 4 million solar masses is an impressive number, but it is not particularly large by the standards of supermassive black holes found at the centers of other galaxies. The black hole at the center of Messier 87, the one imaged in 2019, has a mass of approximately 6.5 billion solar masses, more than 1,000 times more massive than ours. Some quasars, the extraordinarily luminous cores of active galaxies powered by the accretion of matter onto their central black holes, are powered by black holes with masses tens of billions of times that of the Sunday. Our galactic center is quiet by comparison. Sagittarius A Times is not currently an active quasar. It accretes materials slowly and releases energy at a modest rate. There are hints in the structure of our galaxy's central region, vast lobes of hot gas extending perpendicular to the galactic plane, called the Fermi bubbles, that Sagittarius A Times was considerably more active in the past, perhaps several million years ago. But today it sits quietly at the galaxy's center, a dark presence felt primarily through gravity rather than through light. The Milky Way contains somewhere between 100 billion and 400 billion stars. The range reflects genuine uncertainty. Counting stars in a galaxy is not a straightforward exercise, but the order of magnitude is well established. Most of those stars are not like our Sunday. The most common type of star in the galaxy, by a large margin, is the red dwarf, a dim, cool, long-lived star, significantly smaller and less luminous than the Sunday. Red dwarfs burn their fuel so slowly that many of them will outlive the current age of the universe many times over, eventually fading to cold, dark remnants after trillions of years. Sun-like stars, G-type main sequence stars, of approximately solar mass and luminosity, represent only a small percentage of the galactic population. The brilliant blue and white stars that dominate the visual appearance of star-forming regions are even rarer, and they burn fast, living only millions of years before exhausting their fuel and ending in supernovae. The galaxy also contains enormous clouds of gas and dust, the raw material for future star formation. These molecular clouds, some of them tens of thousands of light years across, are the nurseries where new stars are born. When a region within a molecular cloud becomes dense enough, under the influence of gravity or triggered by the shockwave from a nearby supernova, the cloud begins to collapse. As it collapses, it heats up. Eventually, if enough mass accumulates, the temperature at the center rises to the point where nuclear fusion ignites hydrogen atoms fusing into helium, releasing energy in the form of light and heat, and a new star is born. Our Sun formed this way approximately 4.6 billion years ago in a molecular cloud that no longer exists as a coherent structure. The cloud collapsed, formed the Sun and a disk of gas and dust around it, and that disk eventually coalesced into the planets, moons, asteroids, and comets of our solar system. This is the context in which Webb's observations become truly disorienting, because Webb has not just revealed the scale of what lies beyond our galaxy. It has also changed our understanding of the history of galaxies like ours, including the specific history that produced the conditions in which we exist. One of the most important things Webb has revealed is that the process of galaxy formation was, in the early universe, considerably more violent and rapid than the standard model predicted. The galaxies Webb detects at extreme distances, the ones forming within the first billion years after the Big Bang, are not quiet, slow accumulators of stellar mass. Many of them are forming stars at rates that dwarf anything happening in the Milky Way today. Star formation rates of hundreds or even thousands of solar masses per year, meaning the galaxy is producing hundreds or thousands of new suns every year, have been inferred from the luminosity and spectral signatures of some of these early systems. By comparison, our galaxy is currently forming new stars at a rate of roughly 1 to 3 solar masses per year. The early universe was not a calm place, it was a furnace. This matters for our own galaxy's history because the Milky Way is not a pristine, isolated object that formed from scratch in its current location. It is the product of a long history of mergers, accretions, and interactions that stretch back billions of years. Astronomers can read that history in the kinematics, the velocities, and orbital patterns of the Milky Way's stars, and in the chemical abundances of different stellar populations. Stars that formed in the early galaxy carry the chemical signatures of the conditions at the time of their birth. Low abundances of elements heavier than hydrogen and helium, because those heavier elements are produced inside stars over generations of stellar birth and death, and had not yet accumulated in large quantities. Later generations of stars, including our Sun, carry the enriched chemical signatures of multiple prior generations of stellar evolution. Webb has added to this picture by revealing the properties of galaxies at the epochs when the Milky Way's progenitor system, the early proto-galaxy that would eventually become our galaxy, was likely forming. The conditions Webb observes in the early universe at those redshifts are the conditions in which our own galaxy's history began. The violent, rapid star formation happening in those early galaxies is not a foreign curiosity. It is a description of what our own galactic ancestors were doing in some form before the mergers and growth that eventually produced the galaxy we live in today. One of the confirmed findings from Webb that connects directly to this history is the detection and characterization of galactic outflows, streams of gas expelled from galaxies by the collective energy of supernovae and the radiation, pressure from massive stars. When a galaxy forms stars at very high rates, the energy released by those stars and by the supernovae that end their lives can drive powerful winds that blow gas out of the galaxy. These outflows both regulate star formation by removing the fuel for future stars and enrich the surrounding intergalactic medium with heavy elements that later fall back onto galaxies or contribute to the formation of future generations of stars in other systems. Webb's spectroscopic instruments are capable of detecting and characterizing these outflows in detail, even in very distant galaxies, providing direct information about how energy and material were cycling through the early universe. This is not abstract science. The heavy elements in your body, the carbon, the oxygen, the nitrogen, the iron in your blood, were produced inside stars that lived and died before the Sun formed. Those elements were expelled into the interstellar medium through stellar winds and supernova explosions dispersed through the galaxy over millions of years, and eventually incorporated into the molecular cloud that collapsed to form our solar system. You are, in the most literal chemical sense, made from the recycled material of dead stars. And Webb is showing us in unprecedented detail how that recycling process worked in the early universe, how the first stars forged heavy elements, expelled them, and set in motion the chain of stellar generations that eventually produced the conditions for planets, chemistry, and life. The question of life, of whether the universe's scale implies loneliness or companionship, sits at the edge of everything Webb's observations imply, without yet being answerable. The Drake equation, proposed by astronomer Frank Drake in 1961, attempted to estimate the number of technologically advanced civilizations that might exist in the Milky Way at any given time by multiplying together a chain of estimated probabilities: the rate of star formation, the fraction of stars with planets, the fraction of those planets capable of supporting life, the fraction on which life actually arises, the fraction on which intelligent life develops, the fraction that develops detectable technology, and the average lifespan of such civilizations. The equation is not predictive in any rigorous sense. Most of its terms were essentially unknown in 1961 and remain uncertain today, but it established a framework for thinking about the question. In the decades since, several of those uncertain terms have become considerably better constrained. We now know from the Kepler Space Telescope and from subsequent planet-hunting missions that planets are extraordinarily common. Most stars have planets. A significant fraction of those planets orbit in the habitable zone of their star, the range of distances where liquid water could, in principle, exist on a planetary surface. Estimates of the number of potentially habitable planets in the Milky Way alone run into the billions. The universe, it appears, is full of real estate that meets the basic thermodynamic criteria for the chemistry of life as we understand it. Webb has extended this knowledge in a specific and important direction. One of Webb's designated scientific programs involves the spectroscopic characterization of exoplanet atmospheres, the study of the chemical composition of the air, if they have it, of planets orbiting other stars. By observing a planet as it passes in front of its host star, Webb can analyze the starlight that passes through the planet's atmosphere and identify the specific wavelengths absorbed by different molecules. This technique, transmission spectroscopy, allows astronomers to determine, at least in principle, whether a planet's atmosphere contains water vapor, carbon dioxide, methane, oxygen, or other molecules of biological interest. Webb has already produced confirmed atmospheric detections for several exoplanets. The most discussed is the detection of carbon dioxide and other molecules in the atmosphere of a hot Jupiter, a massive planet orbiting close to its star at a level of precision that marks a genuine advance over what was previously achievable. More scientifically significant, though harder to interpret, are the ongoing observations of smaller, rocky planets in the habitable zones of nearby red dwarf stars. The TRAPPIST, one system's 7 roughly Earth-sized planets orbiting a small red dwarf star approximately 40 light-years away, has been a primary target for Webb atmospheric studies. The results so far are tantalizing in their ambiguity. Some of the planets appear to lack thick atmospheres of the type that would be easily detectable, but the absence of a thick atmosphere does not preclude the presence of a thinner one, and the observations are ongoing. The question of whether any of the TRAPPIST-1 planets hosts an atmosphere hospitable to life has not been answered, but Webb is the instrument best positioned to eventually answer it. What does it mean, set against the background of everything Webb has revealed about the scale of the universe, that we are actively searching for life elsewhere? It means that the species conducting this search has not made peace with its smallness. It has not accepted the vastness of the cosmos as a reason for passivity or silence. It has, instead, pointed its most powerful instruments at the nearest potentially habitable worlds and begun asking carefully, systematically, with calibrated infrared detectors and spectral analysis algorithms, whether anyone else is out there. That question will not be answered quickly. The search for biosignatures, chemical signs of biological activity in a planetary atmosphere, is a science in its earliest stages, with a detection technology that is new and an interpretive framework still being developed. A biosignature detection, if it comes, will require extraordinary care in ruling out non-biological explanations before any conclusion about life can be drawn. The scientific community has internalized the lessons of past premature claims and will approach such a detection with corresponding rigor. But the search is real, the instruments are capable, and the universe's apparent abundance of potentially habitable environments makes the question more urgent and more tractable than it has ever been before. There is another frontier that Webb is opening, quieter in its public profile, but potentially profound in its implications for our understanding of the universe's most fundamental composition. That frontier is dark matter and dark energy. Dark matter is the name given to the unknown substance or substances that account for the gravitational effects not explained by the visible matter in the universe. Its existence is inferred from multiple independent lines of evidence. The rotation curves of galaxies, the way stars in the outer regions of galaxies orbit too fast to be held in place by the gravity of visible matter alone, the bending of light by galaxy clusters, the pattern of temperature fluctuations in the cosmic microwave background, the large-scale structure of the cosmic web, and the dynamics of galaxy clusters in collision. Every one of these lines of evidence points to the same conclusion. There is significantly more mass in the universe than we can see. The invisible component dark matter is estimated to make up approximately 27% of the total energy content of the universe. What dark matter actually is remains entirely unknown. It does not emit, absorb, or reflect light. It does not interact through the electromagnetic force. It interacts with ordinary matter only gravitationally, making it invisible to all conventional telescopes, regardless of the wavelength they use. Numerous candidate particles have been proposed, weakly interacting massive particles, axions, sterile neutrinos, and others, but none has been directly detected in laboratory experiments despite decades of search. Dark matter is one of the most well-evidenced and least understood entities in all of physics. Its presence is not seriously doubted by the scientific mainstream. Its nature remains completely mysterious. Dark energy is a separate mystery, and in some ways a more troubling one. In 1998, two independent teams of astronomers studying the light curves of distant Type Ia supernovae stellar explosions used as standard candles for measuring cosmic distances made a discovery that earned a Nobel Prize: permanently altered cosmology. The universe is not merely expanding, the expansion is accelerating. Distant supernovae were dimmer than they should have been if the expansion were slowing under the influence of gravity, as had been expected. They were dimmer because they were farther away than they should have been, because the expansion of the universe had been speeding up over the last several billion years, carrying them farther than a simple decelerating expansion would have placed them. The cause of this accelerating expansion is called dark energy. It is, in the most minimalist description, the energy of empty space, a property of the vacuum itself that produces a repulsive effect counteracting gravity on the largest scales. The current best fit cosmological model assigns dark energy approximately 68% of the total energy content of the universe, dark matter approximately 27%, and ordinary visible matter every star, planet, galaxy, gas cloud, and black hole we have ever detected or catalogued approximately 5%. 5%. The universe is overwhelmingly composed of things we cannot see, do not understand, and have not detected in any direct way. What we call the universe, what Webb is photographing when it captures those deep field images, is the small luminous fraction of a reality whose dominant components are invisible. Webb is contributing to dark energy research through several programs, Type Ia supernovae studies more precise versions of the measurements that originally revealed accelerating expansion are ongoing with Webb's capabilities, providing better calibrations of the distance ladder and potentially new constraints on whether dark energy behaves as a true cosmological constant or varies across cosmic time. Gravitational lensing studies, detailed analyses of how mass concentrations bend the light of background sources, provide independent constraints on the distribution of dark matter and the geometry of space-time, both of which are sensitive to the properties of dark energy. And the large-scale structure surveys Webb contributes to carry information about how dark energy has affected the growth of structure over cosmic time. None of these programs has produced definitive new answers about the nature of dark matter or dark energy. The mysteries remain mysteries, but the constraints are becoming tighter, the measurements more precise, and the space of possible explanations more restricted. At some point, through Webb's observations, or through future instruments, or through laboratory experiments now underway, or not yet conceived, the nature of dark matter will be identified. The nature of dark energy will be characterized. And when that happens, the picture of what the universe actually is, what it is made of, at its most fundamental level, will change in a way that makes the shift from thinking our galaxy was the whole universe to understanding it as one entry among 2 trillion look modest by comparison. The sheer accumulation of scale, from cosmic web to supercluster, to cluster to local group to galaxy, is disorienting enough. But there is another dimension of scale that Webb has made impossible to avoid, and it may be the most humbling of all. That dimension is time. The universe is 13.8 billion years old. The Earth is 4.5 billion years old. The Sun is 4.6 billion years old. Modern humans, anatomically modern Homo sapiens, have existed for approximately 300,000 years. Recorded history spans roughly 5,000 years. Scientific astronomy, in any recognizable modern sense, is about 500 years old. The James Webb Space Telescope has been operational in its primary science mode for approximately 2 years, accumulating a body of observations that has already transformed multiple fields of astrophysics, and will continue to do so for its operational lifetime, currently planned to extend to at least 10 years from launch. The relationship between these timescales is almost impossible to hold in mind simultaneously. 300,000 years of human existence is an eye blink against 4.5 billion years of Earth's age. Earth's age is a third of the universe's age. The universe's age is long enough that the very first stars, the population 3 stars, made entirely of hydrogen and helium with no heavier elements, which formed within the first few 100 million years were born, lived their entire lives, and died in supernovae that seeded the universe with the first heavy elements, all before our galaxy had fully formed. Several complete generations of stars lived and died before the sun ignited. The carbon atoms that make up the organic molecules in your cells passed through at least one stellar interior, and likely several, before being incorporated into the molecular cloud that became our solar system. Webb is observing, directly and in detail, the epochs during which this stellar recycling was in its earliest and most intense phases. The galaxies at extreme redshifts that Webb detects, those impossibly massive, impossibly mature systems in the universe's first billion years, were running their first stellar generations through their full life cycles at a pace and intensity that the current universe does not match. The universe's star formation rate peaked roughly 10 billion years ago and has been declining ever since. We live in a universe that, by the standard of its own history, is now relatively quiet in a mature, middle-aged phase of cosmic evolution, past the wild intensity of its youth, burning more slowly and with greater order than it once did. Our galaxy reflects this. The Milky Way's star formation rate is not 0 new stars are forming now in molecular clouds throughout the disk, and will continue to form for billions of years into the future. But the rate is far below what it was in the galaxy's early history, when it was actively assembling from mergers and accreting large quantities of fresh gas. The galaxy's current relative calm is in part a product of its age. The most readily available gas has mostly been converted into stars or expelled. What remains forms new stars more slowly in a galaxy that is gradually but measurably winding down its most intense period of activity. The future of our galaxy, extended outward across cosmic time, is well described by current astrophysical models, though with large uncertainties at the longest timescales. The Andromeda merger, in 4 to 5 billion years, will disrupt and ultimately transform both galaxies. The resulting Milkomeda will likely be an elliptical galaxy, lacking the organized disk structure of either progenitor, with a population of stars heavily mixed from both original systems. Star formation during and immediately after the merger will likely spike dramatically, triggered by the compression of gas clouds during the interaction, before eventually declining as the available fuel is consumed. In the very long run, on timescales of trillions rather than billions of years, the merged galaxy will gradually exhaust its remaining star-forming material and star formation will cease. Existing stars will continue on their evolutionary tracks, living out their lifespans and ending as white dwarfs, neutron stars, or black holes. After perhaps 10 to 100 trillion years, the last red dwarfs will exhaust their fuel and fade. The galaxy, whatever it has become by then, will be cold and dark. This is the confirmed trajectory of the universe's stellar population, extrapolated forward using known physics. It is a story of gradual cooling, gradual dimming, gradual entropy. The brilliant, star-forming, actively evolving universe we observe the one Webb is documenting in extraordinary detail is the universe in its relatively brief productive phase. Before it and after it lie timescales of preparation and decay that dwarf the current epoch, even as the current epoch dwarfs the span of human civilization. Standing at this temporal intersection born late in the universe's productive phase, equipped for the first time in history with instruments capable of seeing the full scope of cosmic time, the human position is genuinely peculiar. We have arrived at exactly the right moment to observe the universe in its fullest accessible depth, because we have built the technology to do so. A civilization that arrived a billion years earlier would have lacked the heavy elements needed for complex chemistry. A civilization that arrives a trillion years from now may face a universe from which the distant galaxies have accelerated beyond the observable horizon, leaving a night sky with no extragalactic objects, a cosmos apparently consisting of only the local group, with no evidence visible of the vast structure we can see today. We are here observing at the moment when the full scope of the universe is still just barely within reach of our instruments. That is not something to pass over quickly. There is a specific image that keeps returning to the center of this story. Not a metaphor, not an illustration, an actual image. A photograph taken by a telescope floating in space approximately 1 million miles from Earth at a location called the second Lagrange point, where the gravitational pulls of the Sun and Earth combine to create a stable orbital position that allows the telescope to remain in a fixed orientation relative to both bodies simultaneously. The telescope is cold, colder than anything in our solar system. Its detectors chilled to within a few degrees of absolute zero to reduce the thermal noise that would otherwise overwhelm the faint infrared signals it is designed to catch. Its primary mirror is made of 18 hexagonal segments of beryllium coated in a thin layer of gold, arranged into a surface 6.5 meters across and aligned to a precision measured in nanometers. The mirror took years to fabricate, years to test, years to assemble, and then folded itself, origami-like, into the shroud of an Ariane 5 rocket for the journey into space, unfolding again in a deployment sequence so complex and so precisely choreographed that a single failure in any of its 344 individual mechanisms would have ended the mission entirely. That telescope is James Webb, and the image it returned, a deep field image, the kind produced by staring at a single tiny patch of sky for an extended period and collecting every photon that arrives during that time, contains thousands of galaxies in a region of sky so small that you could cover it with a grain of sand held at arm's length. That image is not an illustration of scale. It is not an artist's impression or a computer simulation. It is a photograph of the actual universe as seen from this planet by instruments we built in the year we built them. Hold that image in mind as we arrive at the final reckoning this journey has been building toward. Not a reckoning with numbers we have travelled through enough numbers by now that their power to surprise has been mostly exhausted. This is a reckoning with meaning, with what it implies to be a small thing in a large universe, a late thing in an old universe, a briefly aware thing in a cosmos that was running for 9 billion years before anything on this planet had a nervous system capable of registering its own existence. Begin with what is confirmed and not seriously disputed among researchers. The observable universe spans approximately 93 billion light-years in diameter. It contains on the order of 2 trillion galaxies, 2 million distributed through the cosmic web of filaments, clusters, and voids that constitutes the largest verified structure in existence. Our galaxy, the Milky Way, is one of those 2 trillion. It is classified as a barred spiral galaxy of average mass, roughly in the middle of the galactic mass distribution, neither among the largest nor among the smallest. It contains between 100 billion and 400 billion stars. It is approximately 13 billion years old, formed from the merger of smaller proto-galactic systems in the early universe, assembled by gravity from the density fluctuations that seeded all structure after the Big Bang. Our galaxy belongs to a group of approximately 50 galaxies called the Local Group. The Local Group belongs to the Virgo Supercluster. The Virgo Supercluster is one component of Laniakea, a supercluster 500 million light-years across. Laniakea is one of the large-scale structures of the cosmic web. The cosmic web fills the observable universe. This is the confirmed map assembled over decades of observation using every available instrument, most recently and most precisely extended and refined by Webb. Every layer of this map is supported by independent evidence. None of it is speculation. Against this map, our position is objectively modest. not modest in the sense of requiring philosophical humility to acknowledge modest in the straightforward, measurement-based sense that we are a small galaxy in a large universe, occupying no special location in any of the structures that contain us, having formed late in cosmic history relative to the full span of the universe's age, and located in a quiet, average region of the galactic disk around a star of common type. The Sun is a G-type main sequence star. G-type stars represent roughly 7% of all stars in the Milky Way. The majority of stars in the galaxy are dimmer, smaller, and longer-lived. We orbit at a radius that is typical for stars in the disk. We are not near the center. We are not near the outer edge. We are not in a particularly dense region of star formation. We are not near any large-scale gravitational anomaly that would make our position unusual in any dynamically important way. Everything Webb has done, every image it has returned, every spectrum it has measured, every galaxy it has detected at extreme redshift, every atmospheric molecule it has identified in an exoplanet's air, every refinement it has made to the distance ladder and the Hubble constant and the distribution of matter across cosmic time has deepened and confirmed this picture. The universe is older, larger, more structured, more complex, and more filled with galaxies than previous instruments could fully reveal. Our place within it is exactly what careful measurement suggested it would be: ordinary, unremarkable, peripheral in every quantifiable sense. And yet the story does not end there. It cannot end there, because ending there would mistake the map for the full reality it describes. What Webb's observations cannot capture, what no telescope can image, no spectrograph can measure, no data reduction pipeline can extract from photons, is the fact that any of this is being observed at all. This is not a mystical claim. It is a straightforward observation about what is unusual in the context of everything Webb has shown us. In 2 trillion galaxies, spread across 93 billion light-years, accumulated over 13.8 billion years of cosmic evolution, Webb has found abundant stars, abundant planets, abundant chemistry. It has found the molecular building blocks of organic chemistry in interstellar clouds. It has found water in planetary atmospheres. It has found the conditions, repeated across countless systems, that we associate with the preconditions for life as we understand it. What it has not found, what it cannot directly detect because the relevant signals are far too subtle and far too local, is confirmed evidence of another civilization. Another species that built instruments and pointed them at the dark and asked what was out there. That absence is not evidence of uniqueness. The universe is vast beyond any useful communication of the word vast, and Webb sees only the light that reaches its mirror, which means it sees only the past, only the large scale, only the bright. A civilization on a planet orbiting a star in a galaxy 1 billion light-years away would leave no detectable trace in a Webb deep field image. The galaxy itself would be a smudge of a few pixels, the star utterly invisible, the planet and anything on it so far below the detection threshold as to be meaningless to discuss. The search for life and for intelligence requires different instruments, different methods, different approaches than deep field imaging. SETI programs, direct biosignature detection via transmission spectroscopy, future space interferometers capable of directly imaging Earth-like planets around nearby stars. These are the tools relevant to that question. What Webb has done is establish the scale and the context. It has confirmed that the universe is extraordinarily large, extraordinarily old, and extraordinarily full of the conditions that, on Earth at least, led to life and eventually to inquiry. It has established the 2 trillion galaxy backdrop against which the question of life elsewhere must be asked. And in doing so, it has made 2 incompatible responses to the Fermi paradox, the observation that if intelligent life is common, we should have detected it by now more vivid and more pressing simultaneously. The first response is that we have not detected other civilizations because they do not exist in detectable form, either because life is extraordinarily rare despite the favorable conditions, or because civilizations inevitably collapse before developing the technology needed for detection, or because the communication methods we are listening for are simply not the ones used by civilizations sufficiently advanced to be worth detecting. Against a universe of 2 trillion galaxies, any of these explanations would still leave room for only a single technological civilization at any given cosmic moment. The universe does not require life to be common in order to have produced us. Improbable events, given enough trials across enough space and time, become inevitable. 2 trillion galaxies, most with hundreds of billions of stars, most stars with planets, the number of trials available for any rare process to occur even once is so large that extreme rarity becomes almost irrelevant. The second response is that we simply have not been looking in the right way for long enough with the right tools. Scientific SETI has been practiced in earnest for roughly 60 years, a period of time so short relative to the age of the universe as to be essentially zero. Our technological civilization, defined as the period during which we have been producing electromagnetic radiation detectable at interstellar distances, spans less than 150 years. In the context of a universe 13.8 billion years old, we are newcomers who have been broadcasting for a geological instant. The absence of a confirmed detection after 60 years of limited bandwidth radio searches is not evidence of absence in any universe as large and old as Webb has confirmed ours to be. Both of these responses are rational. Both are supported by the evidence, or rather by the absence of the specific evidence that would rule either out. The question remains open genuinely, scientifically open, in a way that is unusual for questions that have been asked this persistently for this long. Webb has not answered it. It has, by establishing the true scale and composition of the universe, made it more answerable in principle and more urgently worth pursuing in practice. Return, for a moment, to the numbers, not to be numbed by them again, but to use them differently this time as a way of appreciating the specific, improbable, almost absurd sequence of conditions that produced something capable of registering them. The universe is 13.8 billion years old. The first stars formed within the first few 100 million years, massive, brilliant, short-lived stars made entirely of hydrogen and helium, containing no heavier elements. When those first stars ended their lives in supernovae, they expelled their nuclear ash carbon, oxygen, neon, magnesium, silicon, sulfur, calcium, iron into the surrounding gas. Second and third generations of stars formed from this enriched material, fusing heavier elements in their cores and expelling them in turn. Over successive stellar generations, the heavy element content of the interstellar medium built up gradually and unevenly, concentrating in the disk regions of galaxies where star formation was most intense. By the time our galaxy was approximately 9 billion years old, roughly 4.5 billion years ago, the interstellar medium in our region of the Milky Way contained enough heavy elements to form not just stars, but rocky planets. The molecular cloud that collapsed to form the Sun and our solar system had been enriched by multiple prior generations of stellar nucleosynthesis and supernova dispersal. The carbon in every organic molecule on Earth, the oxygen in the atmosphere, the iron in the planet's core and in your blood, the silicon in the rocks and the soil, all of it was forged inside stars that no longer exist and scattered across space in their deaths. Our solar system formed from the recycled material of those dead stars, assembled by gravity into a new system with a new star at its center and a set of planets, including a rocky one at just the right distance from its star for liquid water to persist on its surface under the right atmospheric conditions. Life on that rocky planet, whatever its ultimate origin, whatever the specific sequence of chemical reactions that first produced a self-replicating molecule, has been evolving and diversifying for approximately 3.8 billion years. In that time, it has produced an extraordinary range of forms, biochemistries, and behavioral repertoires. Only in the last few 100,000 years did it produce a species capable of sustained, symbolic reasoning, capable of building mental models of things not immediately present, of accumulating knowledge across generations through language and writing, of asking questions about things beyond any immediate practical utility. That species spent most of its existence unaware that the faint streak of light across the night sky was a galaxy, unaware that galaxies existed, unaware that anything lay beyond the bounds of what could be seen from Earth with the naked eye. It has been aware of the full scope of the cosmos, even approximately for less than 100 years. It has been capable of observing the early universe directly through infrared telescopes sensitive enough to detect light from the first billion years of cosmic time for approximately 2 years. In those 2 years, it has rewritten the population estimate for galaxies from 200 billion to 2 trillion. It has detected impossibly massive galaxies in the universe's first billion years that challenge the standard model of structure formation. It has measured the Hubble constant with unprecedented precision and thereby sharpened the tension between two methods of determining the universe's expansion rate into one of the most interesting, unresolved problems in physics. It has taken the first detailed atmospheric spectra of potentially habitable exoplanets. It has observed the cosmic web in greater detail at higher redshifts than any previous instrument. It has produced images of our own galactic center, of star-forming regions, of interacting galaxies, of galaxy clusters, and of deep fields, each one revealing aspects of the universe's structure and history that no previous instrument could access. 2 years against 13.8 billion. The disproportion is almost funny, if funny is the right word for something that simultaneously diminishes and elevates in equal measure. Webb has also done something that resists easy categorization in a purely scientific framework. It has produced images of extraordinary aesthetic power. This is not irrelevant to the story it is telling. The pillars of creation, first imaged by Hubble in 1995 and re-imaged by Webb with dramatically higher resolution in 2022, are towering columns of gas and dust in the Eagle Nebula, approximately 6,500 light-years away, within which new stars are actively forming. Webb's image of the pillars shows them in infrared, revealing details invisible to Hubble. Newly formed protostars embedded in the dense gas, glowing faintly as their gravity compresses the surrounding material toward the temperatures at which nuclear fusion will ignite. The image looks, to any observer who has spent time with it, like something from a mythological tradition, vast, ancient, luminous columns standing in a dark sky, generating new suns in their depths. It is not an artistic rendering. It is a scientific image produced by a calibrated infrared detector array. But it carries an aesthetic charge that no amount of calibration removes, because the universe is genuinely, structurally beautiful in ways that map onto human aesthetic sensibility, regardless of whether that mapping was ever intended by anything. The Cartwheel Galaxy, a ring galaxy produced by the collision of two galaxies hundreds of millions of years ago, appears in Webb's image as an almost perfect bullseye of glowing material with an outer ring of intense star formation surrounding a relatively quiet inner region. The collision compressed gas clouds throughout the galaxy, triggering star formation in a ring that expanded outward from the impact point like a ripple in a pond. Webb's image captures this structure with a clarity that makes the physics viscerally legible. You can see, just by looking, how the collision produced the ring, how the ring is actively making new stars, how the galaxy's future structure is being written in real time by the dynamics of an event that happened hundreds of millions of years before the first dinosaur walked on Earth. Stephan's quintet, a compact group of 5 galaxies in the constellation Pegasus, shows, in Webb's image, the largest infrared image the telescope has produced, a sprawling, complex scene of gravitational interaction, gas heated by shock waves, star formation triggered by the collision of gas clouds from different galaxies, and a background of thousands of additional galaxies visible in the surrounding field. The image is so detailed that different regions of it support different scientific papers, different analyses, different questions about what is happening and why. These images are not decorative. They are data. Every photon that contributed to them carries information about temperature, velocity, composition, distance, and the physical processes that produced the light. But they are also, without any contradiction, among the most beautiful things the human species has produced, not because they were designed to be beautiful, but because the universe, filtered through Webb's mirrors and rendered into visible wavelengths by the software processing pipelines developed by hundreds of scientists and engineers, looks like this. This is what it looks like. This incandescent, complex, enormous, ancient, structured, ongoing, luminous thing. What does it mean for a galaxy to be small? This question is worth sitting with longer than it might seem to deserve, because the answer is not obvious, and the easy answer is almost certainly wrong. The easy answer is that smallness implies insignificance, that a galaxy containing 100 to 400 billion stars, orbiting for 13 billion years, containing within itself the conditions for the origin of life and intelligence and inquiry, is somehow diminished by the existence of other galaxies larger than it, or by the existence of 2 trillion galaxies in a universe 93 billion light-years across. But significance is not a property that scales linearly with size. It is not a property distributed evenly across mass. It is not found in higher concentrations in larger structures than in smaller ones. A galaxy 100 times the size of the Milky Way is not 100 times more significant than the Milky Way in any sense of the word significance that actually holds up under examination. IC 1101, the largest known galaxy, spanning approximately 6 million light-years, compared to our galaxy's 100,000, is 100 times larger than ours and, as far as we know, contains no observers, no instruments, no species that has asked how large it is or why. It is massive, it is ancient, it is impressive by any size-based metric. It is, as far as current knowledge extends, completely unaware of its own existence. The Milky Way is small. That is a confirmed, measurement-based fact. It is also the only galaxy, the only object at any scale, in the entire observable universe that we know for certain contains something that has built a mirror and pointed it at the dark and asked what is out there. That asymmetry does not resolve the philosophical question of significance. It does not prove that the Milky Way is special in any cosmic sense, or that life is common elsewhere but simply undetected, or that the universe has any purpose or direction or preference for awareness over emptiness. It proves nothing except this, that here, in this small galaxy, around this ordinary star, on this unremarkable rocky planet, something developed the capacity to want to know, and to build tools adequate to the knowing, and to be genuinely astonished by what those tools revealed. That astonishment is not a small thing, not because it has cosmic significance in any measurable sense it may not, but because it is, of all the processes and phenomena Webb has documented and measured and refined, the one we have the most direct access to. We do not experience the formation of a galaxy at high redshift. We do not feel the gravitational pull of the great attractor. We do not observe the expansion of space. But we do experience the astonishment directly, immediately, in a way that no instrument mediates. The astonishment is what is happening right now, in the mind that is encountering these numbers and these images and these scales for the first time or the 100th time, and finding every time that the universe is larger and stranger and more structured and more ancient than any prior encounter had made fully real. Webb's story is not finished. It has been operational in its primary science mode for a period measured in years. Its designed operational lifetime extends to at least 10 years from launch, and possibly significantly longer, depending on the precision with which the telescope was placed in its initial orbit, a precision that determines how much fuel remains for station-keeping maneuvers. Early assessments of the launch trajectory were encouraging. The telescope was delivered to its destination with such accuracy that the original 10-year fuel budget may support a mission lifetime closer to 20 years. If that estimate holds, Webb will be collecting data until the middle of the 2040s, accumulating an observational legacy that will shape astrophysics for generations. In the time remaining, Webb will extend and deepen every line of inquiry it has opened. The early massive galaxies will be studied in greater spectroscopic detail, producing better measurements of their stellar masses, star formation histories, chemical compositions, and structural properties. Those measurements will progressively constrain the theoretical explanations competing to account for them, and will eventually either support a modest revision of the standard model or point toward something more fundamental. The Hubble tension will either be resolved by the identification of a systematic error in one of the measurement methods, or it will harden into a confirmed discrepancy that demands new physics. Webb's atmospheric studies of exoplanets will extend to smaller, cooler, more Earth-like targets as observational techniques are refined and longer observation campaigns are executed. The cosmic web will be mapped in greater detail at earlier epochs, filling in the period between the Big Bang and the universe we can currently observe with the most detail. Dark matter halos around galaxies and galaxy clusters will be studied through gravitational lensing with precision not previously achievable. The zone of avoidance, that region of our own sky blocked by the plane of our galaxy, will become progressively less opaque in infrared wavelengths, revealing more of the large-scale structure hidden behind the Milky Way's disk. Future missions will extend what Webb has begun. The Nancy Grace Roman Space Telescope, scheduled for launch in the coming years, will conduct wide-field infrared surveys, covering areas of sky thousands of times larger than Webb's focused deep fields, identifying statistical samples of objects that Webb can then study in targeted follow-up observations. The planned Habitable Worlds Observatory, a future NASA flagship concept, is designed specifically to directly image Earth-like planets around nearby stars and search their atmospheres for biosignatures at a level of sensitivity and completeness not achievable with Webb. The extremely large telescope and other next-generation ground-based observatories will complement space-based instruments with their enormous collecting area and advanced adaptive optics systems. The James Webb Space Telescope is not the end of this story. It is one chapter of a longer investigation that will outlast everyone currently alive and extend as far into the future as the species chooses to pursue it. Every answer Webb provides opens new questions. This pattern, which might seem frustrating to someone who wants the investigation to conclude, is actually the clearest possible indicator of science working at the boundary of what is known. The questions Webb is opening are better questions than the ones it answered. They are more specific, more quantitative, more directly connected to the fundamental structure of the universe than the broad questions that motivated its construction. That is how genuine scientific progress works. Not by achieving complete understanding and then stopping, but by replacing coarse ignorance with refined ignorance, by knowing enough to ask better questions, to identify smaller and more specific uncertainties, to design the next generation of instruments around the gaps that the previous generation revealed. The gap between what Webb is showing us and what our theoretical frameworks fully account for is not a sign of failure. It is the productive edge of knowledge, the place where the universe is telling us that there is more to understand, that the models need extension or revision or replacement in specific ways that better data will eventually clarify. The impossible galaxies are not refuting the Big Bang. They are refining our understanding of what happened in the universe's earliest epochs, pushing the theory into territory it had not yet been fully tested in. The Hubble tension is not breaking cosmology. It is pointing toward either a systematic error in one of our measurement chains or a piece of physics not yet incorporated into the standard model. Either resolution will constitute genuine progress. Either outcome will leave us with a more accurate and more complete picture of the universe than we currently have. That is the situation we are in. A species approximately 300,000 years old, having developed science as a systematic practice approximately 500 years ago, and having launched the instrument responsible for its current deepest view of the cosmos approximately 2 years ago, is standing at the edge of its own knowledge and finding that the universe is larger, older, more structured, more full of galaxies, and more full of mystery than any prior instrument revealed. Every direction Webb points contains surprises. Every deep field contains structure where emptiness was expected. Every early galaxy contains more mass and more complexity than the models predicted. Every precise measurement sharpens a tension between different ways of knowing the same thing. This is not the universe politely conforming to our expectations. It is the universe being what it has always been: vast, complex, ancient, stranger than any model we have built so far, and Webb is the instrument that, for the first time, has the sensitivity and the range and the wavelength access to see that strangeness clearly enough to measure it. Step back one final time, all the way back to the full scale of the observable universe, 93 billion light years, 2 trillion galaxies, 13.8 billion years. Imagine the cosmic web as it can now be described with some confidence. Filaments, hundreds of millions of light years long, connecting at nodes where the great superclusters anchor the structure. Voids of near emptiness, stretching hundreds of millions of light years across the spaces between, the whole thing evolving slowly now in the universe's mature phase compared to the violent, rapid assembly of its youth. Somewhere in that web, in a modest filament, in a supercluster called Laniakea, in a cluster called the Virgo Supercluster, in a small group of 50-odd galaxies called the Local Group, sits a barred spiral galaxy 100,000 light years across. Inside that galaxy, in a minor spiral arm, approximately 26,000 light years from a quiet supermassive black hole at the center, a star of average mass and average luminosity sits at the center of a small system of 8 planets, numerous moons, and a belt of smaller rocky and icy bodies. The third planet from that star is rocky, water-covered, approximately 4.5 billion years old, wrapped in a thin layer of gas capable of sustaining liquid water on its surface, and inhabited by a species that has, in the last 500 years, figured out most of the laws governing the behavior of matter and energy. In the last 150 years, built instruments capable of detecting electromagnetic radiation from across the observable universe. In the last 60 years, placed telescopes above the atmosphere to see wavelengths that cannot penetrate to the ground, and 2 years ago began receiving data from the most capable infrared space telescope ever constructed. That telescope is showing us what the universe actually looks like. Not an approximation, not a crude sketch, not a handful of data points from which a rough picture can be inferred, but a genuine, detailed, high-resolution portrait of the cosmos across 13 billion years of its history. The portrait is still being assembled. It will take decades to complete. It will be refined and extended and corrected by every new observation cycle, every new instrument, every new technique developed by the scientists who will spend their careers working with Webb's data and building the instruments that come after it. But the core message of the portrait is already clear, already unambiguous, already confirmed at a level of detail and precision that no earlier instrument could approach. The universe is ancient. It was already building stars and galaxies in the first billion years after the Big Bang, at a pace and with a complexity that surprised the researchers who observed it. The universe is large, beyond any scale that human intuition can genuinely accommodate, and full of galaxies, full of stars, full of planetary systems, full of the chemistry that, on at least one planet, led to life and eventually to the kind of mind that builds telescopes. The universe has been doing all of this for so long and at such scale that any individual human life, any individual human civilization, any individual galaxy is reduced to almost nothing by the comparison. And yet, the universe does not know how large it is. The cosmic web does not contemplate its own structure. The supercluster, Laniakea, does not wonder about the great attractor that pulls its galaxies into a shared motion. The 2 trillion galaxies distributed through the observable universe do not look at each other and ask what they are, where they came from, or how long they have been there. They simply exist, pulling, colliding, forming stars, dispersing elements, evolving across cosmic time in ways governed entirely by physics and geometry, and the initial conditions set at the beginning of everything. The astonishment, the specific experience of encountering this scale and being genuinely moved by it is happening here, in this galaxy, on this planet, in the consciousness of whichever human being is, at this moment, taking in this story and allowing the numbers to do what numbers of this magnitude can sometimes do when they are given enough context and enough time. Stop being numbers and start being something closer to a felt sense of reality. That is what Webb has given us, above and beyond the revised galaxy counts, the resolved spectral lines, the refined distance measurements, the detected atmospheric molecules, the challenged theoretical models. Webb has given us a new felt sense of the scale of what we are part of, not as an abstraction encountered in a textbook, but as a direct, empirical, data-based revelation delivered in photographs that no human eye designed to detect them, processed by algorithms no human hand wrote directly, and assembled into images that nevertheless communicate something immediately and powerfully to any human being who looks at them. The Milky Way is small. It was always small. The universe was always this large, this full, this old, this structured, this extraordinary. We simply lacked the eyes to see it. Webb gave us those eyes, and what we have seen through those eyes is not a diminishment. It is the universe as it actually is the real thing, in its full and almost incomprehensible scale, held briefly in the attention of one small, late, aware species in one unremarkable corner of one minor galaxy, looking out from a planet it did not make. Through mirrors it did. We are small. The universe is enormous. And for a brief, peculiar, astronomically improbable moment, the enormous universe is being seen clearly by something small enough to be astonished by it. That moment is now. That instrument is Webb. And that astonishment, precise, measured, data-driven, and still somehow beyond all measurement, is the most human thing happening anywhere in the observable universe that we currently know about. The mirrors are still open. The data is still coming in. The story is not finished. It is, in every meaningful sense, just beginning.